Hello and welcome to this video on Time Travel 101. So, have you ever wondered if time travel is possible? In this video, we'll explore the concept of time and how it is measured, the theory of relativity and its impact on space-time and the flow of time, and the feasibility of time travel. So here you can see in front of you, these are some of the topics, well, that we'll be going through. I just put intro in there, so just for the sake of it. We'll be talking about the concept of time, the relativity and space-time. By the way, this is where the most of the mathematics will be involved. And just a warning that there will be quite a few mathematics involved in this video. And then finally, we'll talk about the feasibility of time travel. So again, the concept of time will be introduced, and I'll explain how time is measured and how is it represented mathematically. The theory of relativity and its impact on space-time and the flow of time will also be discussed in the video. Now, the concept of time dilation arises, and that we will also explain and quantify it mathematically. Again, the feasibility of time travel is analyzed and will show that traveling to the future is theoretically possible through time dilation, but it is not practical with the current technology. Anyhow, traveling to the past is more complicated, right? And well, it has been for a very long time been subject of intense scientific debate, with one proposed solution that is being the idea of a wormhole. However, the existence and stability of wormhole remain uncertain, and their use for time travel is currently beyond our technological capabilities. Overall, this video is going to provide you with a comprehensive overview of the science of time travel and its current limitations as well. Now, the idea of time travel has long fascinated people, both in science and in the pop culture. The ability to travel to the past or the future has been explored in countless books, movies, and TV shows. However, time travel is actually possible. And if so, what are the physical limitations and requirements for it to become a reality? So this is the question that we would be focusing on. And again, in this video, we'll be talking about the science of time travel and the feasibility from a mathematical physics perspective. All right, so before we can dive into the possibility of time travel, we need to have a clear understanding of what time is and how is it measured, right? So that's where we'll start with the topic of the concept of time, right? And this time is a fundamental concept in physics and is usually defined as a dimension in which events are going to happen in a sequential order. So this sequential order may be, so this is the first event, the second event, the third event, and the fourth event. So all of these are just events, and they're happening one after another in a sequential order. Now, the most common way to measure time is with a clock, as everybody is aware of it, which is just any device that can count and record the passage of time. So it doesn't really have to be your normal clock that you have on your wall. It can be any device that can count and record the passage of time. Now, doing that can be done in multiple ways. We're not going to talk about it right now in this video. But from a mathematical perspective, time is typically represented by the coordinate t. So this t is the coordinate. In your coordinate system, you have x, y, and z. You must be familiar with this coordinate system, right? So x could be one of this axis. So maybe this is x-axis. This vertical axis is your y-axis. And the axis that goes inside and outside is your z-axis. Now, that's where there is another axis or the dimension, which is time, t. And it is used in conjugation with the three spatial coordinates, x, y, and z. And together, they form a four-dimensional coordinate system, t, x, y, and z. You can see these are four dimensions, 1, 2, 3, and 4. And this thing is what we call space-time. So I hope that tells you something about what a space-time is, right? So it's all of these coordinates combined together. This one t is called the temporal coordinate or the time coordinate, while x, y, and z are your spatial coordinates. They carry the information about the space. This is where we can talk about relativity and space-time. Now, In the early 1900s, Albert Einstein introduced to us the theory of special relativity. This theory of special relativity fundamentally changed our understanding of spacetime and how it is related to the concept of time. Now, according to this theory of special relativity, time is not absolute and universal, but it depends on this observer's relative motion. So, for example, if this is an observer and if he is moving relative to something, so suppose he's moving with some velocity and relative to maybe there's another person that is standing, and let's suppose that he is stationary. This person is moving relative to this person. So if he's stationary, he sees him moving with this speed v. Let's assume that for now, right? So what I'm saying is that according to special relativity, the time that passes is not universal or absolute. It depends on the observer's relative motion. So if it depends on this velocity, the time depends on the velocity. So if the velocity is higher or lower, then you can tell how much time has passed, right? So how time moves. So in particular, the theory of relativity predicts that time passes more slowly for objects that are moving at high speeds relative to a stationary observer. So if this velocity is high, then time moves slow. If time moves slow, that means that t will have a larger value. T will be large. Well, I apologize, it would be slow really, right? So if it's slow, t will be small. Right. Now, this thing that we have talked about, it is called time dilation, right? So let's move a bit down over here. This time dilation, we can write this mathematically, right? But we can quantify it with t prime is equal to the original time t divided by a factor, and I'll talk about this factor as well, square root 1 minus v squared over c squared. In this expression, this is the expression for this time dilation, this effect that we just talked about over here, right? Now, this t prime is the time that is measured by the moving object. So in this example, this person who's moving, t prime is the time that he measures, right? And what is t? T is the time that is measured by this stationary observer for whom the velocity is 0. So what is v then? V is the relative velocity between the two objects, right? So between these two objects, what is the relative speed? That's v. And c is simply the speed of light. Right. Now, there's more to the story. That is the theory of general relativity that was developed by Einstein a few years later, expanded on this idea by showing that the presence of massive objects such as planets or stars can also affect the flow of time. So it's not just the speed, it is also the mass. Presence of mass will change or will affect the flow of time. Specifically, general relativity predicts that time passes more slowly in the regions of strong gravitational fields. So for example, if I have a mass in space-time, and if I'm anywhere in this region of this mass, and suppose that this mass, well, let me draw another one. There is another mass that is relatively smaller, right, over here. Let's say this is, so this is capital M and this is small m. Let's use another color of highlighter, and let's say that this is the region around this mass. Right, now if you are in this green region, suppose if there is one person who is in this green region and there is another person who is in this red region. According to what I just said, for this person who is in the green region near a more massive object, then because the mass is higher, the gravitational field will be stronger, and time hence passes slowly for this person in the green zone. However, for this person who is in this red zone near a smaller mass means weak gravitational fields, so time will relatively pass more quickly for him compared to this person. right? Now, I hope that makes sense. Another example you could have thought of could be of a black hole. Near a black hole, time passes very slowly. Why is that? Simply because black holes are very massive, right? So the mass of the black holes is huge. That's why time passes very slowly near a black hole. So, by the way, a little mental exercise for you. Can you think of making a time travel machine, sort of, by this understanding that time moves slowly near a region of strong gravitational field, such as a black hole? So just think about it and you leave your answers in the comment section below. Now, we'll consider two reference frames, right? And one will be stationary. So let me draw it over here. Let's do this. So this is a frame of reference. That is just your coordinates, right? So this is one of it. And let's say that one of these frame of references is moving. So there are two frames of reference. And let's say that this one is moving relative to this one. So this is first and this is second. Right. Now again, one of these frames, frame one is stationary and the other one is moving with a constant speed relative to the stationary frame. Now let's say that a clock in the stationary frame measures a time interval of t. So there's a clock in this frame and it measures some time t for an event that happens. While a clock in the moving frame measures the time interval t prime. So according to special relativity, the two time intervals are related to each other by the following equation that states that t prime is just equal to t over gamma. Now, what is this gamma? This is the factor that we saw over here as well. This is what gamma is. It is known as the Lowrance factor. So you can say that this is just t over square root of 1 minus v squared. Oh, sorry. Let me just rewrite this thing once again. This Lorentz factor gamma, let me write this factor down over here for you. It's defined as the inverse of the square root, right? So it's like this, 1 over 1 minus v squared over c squared, right? So that would mean that this thing is just a t times square root of 1 minus v squared over c squared. Right, now to derive these equations, we'll start with the postulate that the laws of physics are same in all inertial reference frames, right? So if your frame of reference is inertial, then the laws of physics are the same in all of those frames. So let's say that the two reference frames are aligned along the x-axis and they're moving, the moving frame is moving in the positive x direction relative to the stationary frame. Let's also say that the two frames are synchronized at time t equals 0. So when time t is equal to 0, both of them are at the same position. When the moving frame passes the stationary frame, that's when the time t is equal to 0. So when they're on top of each other, t is equal to 0. At this moment, a light pulse is emitted from the origin of both the frames in the positive x direction. So when these two frames are on top of each other, then a light pulse is emitted. So let me see if I can show that. So let's say here the two frames are aligned on top of each other, then a light pulse is emitted. So maybe you can just say when this is the case, that's when this light pulse is emitted. Now, the pulse travels in the positive x direction, and in the stationary frame, the light pulse travels a distance of, so again, this is for the stationary frame. The light pulse travels a distance of x equals ct. Remember that for stationary frame, we are not using primed coordinates, but for the moving frame, we are using prime coordinates. So anything that I write like this, so there are no prime coordinates, it should be noted that that is for the stationary frame. So it travels this distance, x equals c times t in time t. C is again the speed of light, right? So this is a light pulse. That's why the speed is c, and we are just multiplying with time, so we get the distance. This is simple physics, by the way. You know that formula for velocity is equal to distance over time, right? So if you rearrange this thing for distance, you get velocity times time. But this is the light pulse, so the speed is the speed of light. So I just write it like this. So that's where you get this x equals ct from, right? So it does this in time t. And now in the moving frame, the light pulse travels a distance of x prime is equal to ct prime, right? Since the time coordinate for that frame is t prime, and the x coordinate will also be x prime, by the way, right? And this happens in time t prime. Now, according to the principle of relativity, the speed of light must be the same in both frames. So if the speed of light is same in both frames, that means that c, if I can make c the subject of this equation, you get x over t. But since both c's are the same, this is just equal to x prime over t prime. Now, if I substitute x equals ct and x prime equals ct prime in these expressions, you get t prime over t is equal to 1 over gamma. That's where we got, that's how or why I wrote this equation, right? So now if you just bring this t on the other side, it becomes t over gamma. T over gamma equals t prime, right? So this gives us our equation that we started with. Now, we are going to also derive this Lorentz factor. Let's do that. So to derive the expression for the Lorentz factor, we'll use the Pythagorean theorem in space-time. So in the stationary frame, the space-time interval delta s squared, this is the interval between two events that are separated by some distance. So let's suppose that this is your frame. So let me draw it once more, something like this. And there are two events. This is event 1 and this is event 2. And these two events are separated by some distance. Well, let's just keep them on the same axes like this. And they're separated by some distance, let's say delta x, right? So it is the change in the position from 2 and 1. Right. So if they're separated by this distance delta x in space and a time interval, right? So there is well, I should have let it be over here, since if this is my time axis, then this event over here happens over here, and they're separated in both ways in delta x. So you see there's change in x and there's some change in time, right? So delta t is also there. So if that is the case, then this delta s squared is given as c squared delta t squared minus delta x squared, right? So all this is the space-time interval between the two events that are happening. Now in the moving frame, the distance delta x prime is contracted by a factor of gamma due to length contraction. So the space-time interval delta s prime squared, in that case, delta s prime squared is equal to c squared delta t prime squared minus, now the position will be contracted, right? Since it's because of length, the concept of length contraction in the moving frame. So if you're moving, length is also contracted. So we'll multiply that change in length by a gamma factor, but because the change in length is 2 times, right? I mean it's squared, so the gamma is also squared. The Lorentz factor is squared. Right. Now, since the space-time interval is an invariant quantity, this interval is an invariant quantity. It doesn't matter how delta x and delta t are defined. This delta s is going to be constant, right? Now, what does that mean? That means that if the coordinates of these 2 points change, but these are two events, right? These two events, the separation between these two events is not going to change. Right, so if that is the case, then we can equate these two equations, since delta s squared and delta s prime squared is exactly the same, then this would give you c squared delta t squared minus delta x squared is equal to c squared delta t prime squared minus gamma squared delta x squared. Now, assuming that the two events are simultaneous in the stationary frame that is not moving, then you will have delta t is equal to delta t prime. The times are the same, right? If the two events are simultaneous, then you can just solve this thing for gamma, and you would see that you would get gamma is equal to 1 over square root 1 minus v squared over c squared. And that is the derivation of the Lorentz factor. Right, so while we're at it, we can talk about Lorenz transformation. This is something that if you have these two frames, right, that we have been talking about so far, so one of them is moving and one of them is stationary. So let's suppose the first one is stationary and the second one is moving with some speed, right? So if I measure some coordinates in this one, x prime, let's call it x prime, and let's say t prime, and in this one, in the stationary frame, they would be x and t. Let's include for all spatial, so we would have y and z as well, so y prime and z prime as well over here, right? So now the question is, what is there any relationship between these coordinates, right? So are x and x prime related? Are y prime and y or y prime related? Z and z prime, are they related? What about t and t prime? Are they related? So if you want to change or go from one coordinate system to the other one, how do you do that? The answer to that is your Lorenz transformation. So again, you say that you have two frames that are aligned along the x-axis and that the moving frame is moving in the positive x direction with some velocity relative to the stationary frame. Then these are the coordinates, and these coordinates can be linked together. So just to avoid a very congested mathematics, I'm just going to write down these relations for you, and then we can talk about the feasibility of time travel according to all of these things that we have mentioned so far. So the transformation, if I am sitting in x frame, then I know my x in the stationary frame, then I know the x coordinate, this coordinate, and it is minus v times t. I'll know this the velocity, or I can observe from my frame, I can observe the velocity, that would be the relative velocity of the moving frame, right? So that v is also measurable. T I can measure in my frame on my clock, and then this thing is divided by the Lowrance factor thing, that is 1 minus v squared over c squared. So that's how x and x prime are related. Now, for this specific example, since the motion is happening in x direction, since this is the x-axis, then there is no motion that happens in the y or z-axis. What does that mean? That just means that y prime is just the same as y. There is no change in that coordinate. And similarly, z prime is also z. There is no change in the z coordinate as well. However, for the time coordinate, that changes, and it changes in this way, that t prime is equal to t minus v over c squared times x divided by the Lorentz factor thing, 1 minus v squared over c squared. Again, you see that if you are sitting in the stationary frame, then you can have this measure time in that stationary frame t. You can measure the velocity, the relative velocity of the moving frame as well. The position can also be measured in your frame, and then you can just do this mathematics to get the t prime for this thing. Now, these equations that I have written down over here, they describe how the coordinates of an event in one inertial frame are related to the coordinates of the same event in another inertial frame that is moving relative to the first frame with, again, a constant velocity. Now, these are the foundation of the theory of special relativity and have many important applications, such as in the study of high energy physics, cosmology, and behavior of particles at relativistic speeds as well. So with that, we can talk about the feasibility of time travel. Now, given these fundamental principles of relativity and space-time that we have talked about, is time travel actually possible? Now, the answer to that question depends on how you define time travel, right? So first, let's talk about traveling to the future. Right, so the idea of traveling to the future is relatively straightforward from a mathematical point of view. As we have seen, time dilation predicts that time passes more slowly for objects that are moving at high speeds. Remember, if we go back over here, that's where we talked about it. So if you're moving at a high speed or near a strong gravitational field, then time will pass very slowly, right? And it speeds up if the mass becomes small or if your speed becomes small. So therefore, if we can find a way to accelerate an object to a speed of light, or well, not to the speed of light, but very close to the speed of light, or maybe put it in a very strong gravitational field, then we can effectively send that object into the future. So you see, there is no problem theoretically for doing that. All you need to do is somehow find a device to accelerate the person closer to the speed of light, or just maybe find some very strong gravitational field. By the way, that could be near a black hole, right? Then we can effectively send that object into the future. Now, for example, imagine that if we build a spacecraft that can travel at 99% the speed of light, that seems very good, right? But this kind of time travel is not very practical for human beings, as of course it requires enormous amounts of energy. How would you accelerate something to 99% of speed of light? You would need energy. and it requires so much energy that the energy becomes very higher and higher and higher, and you cannot really go to that 99% of the speed of light. And technological advancements as well that are currently beyond our reach. Okay, with that, what about traveling to the past? Well, for the future, we have seen more or less that it is possible, right? What about to the past? The idea of traveling to the past is more complicated and has long been the subject of intense scientific debate. One of the most famous theoretical solutions to this problem is the idea of a wormhole, which is a hypothetical tunnel-like, well, let me first write this thing down over here, that one of the solutions is a wormhole, right? So what is a wormhole? It is a tunnel-like structure that connects two distant points in space-time. So suppose if this is your space, this is your space-time, and one point in space is over here and the other one is over here. Suppose these are the 2 points. What I can do is I can kind of wrap this space-time in such a way that this space-time becomes like this. Well, my drawing is very bad, but these 2 points are like this, and you bring them very closer together. So you can already see that the distance between these 2 points have decreased in this example. And so that's how you connect those two distant points in space-time. Now, according to general relativity, massive objects can wrap space-time, and if the curvature of space-time is extreme enough, then it could potentially create a shortcut or tunnel between 2 points in your space-time. So the concept of using a wormhole to travel through time involves accelerating one end of the wormhole to near to the speed of light while keeping the other end stationary. So one end of this hole should be traveling at very high speeds, while the other end should be not moving at all. So time dilation predicts that time will pass more slowly for the moving end of the wormhole, effectively creating a time difference between the two ends. However, even if such a wormhole were to exist, the amount of energy required to keep one end stationary while accelerating the other to near the speed of light is currently far beyond our technological capabilities. Additionally, the existence of wormholes is purely theoretical, at this point at least, and has not been observed or confirmed by any experimental evidence. Right, so with that, I'm going to wrap up this video by giving a little bit of concluding remarks. Let's start with that the concept of time travel has captured our imaginations for decades. But from a mathematical perspective, it remains highly theoretical and currently beyond our technological capabilities. While the laws of relativity and space-time do allow for the possibility of time travel, practical applications for human beings are still a long way off. Nonetheless, the pursuit of understanding and exploring the concept of time travel remains a fascinating and important area of research in physics and mathematics.